Due to constantly increasing population and consumption, human-caused marine debris is entering the ocean at an ever-increasing rate. This debris consists of glasses, metals, and plastics, and has a variety of detrimental effects both on the marine ecosystems and on the populations that rely on these systems as a source of food. On a global scale, 50 to 80% of the debris entering the ocean is some kind of plastic. And 80% of this plastic debris comes from land-based sources and enters through rivers. While there are many efforts to reduce this debris, such as anti-littering campaigns, banning single-use plastics, and beach cleanups, the rate at which plastic enters our oceans is still increasing. Therefore, it is imperative that more direct solutions be implemented to remove and prevent these plastics from reaching the ocean. This problem has adverse effects on the marine ecosystems it affects, as many species are physically harmed by both the ingestion and entanglement of these plastics. The exposure of larger plastics to the ocean environment causes them to break down into smaller microplastics, which are defined as any plastics smaller than 5 millimeters. These microplastics contain chemical contaminants and can be ingested by many marine organisms. One study found a concentration of up to 2.1 trash items per fish in a certain area. As these plastics make their way up the food chain, the concentration of plastics increases, and by the time it enters the seafood consumed by humans, it can range from 0.7 to 30 milligrams per 100 gram. There are current solutions aimed at collecting marine debris, both in rivers and in the ocean. These solutions, however, are often prohibitively expensive and lack the capability of sorting the trash it collects. Without this functionality, much of the debris collected by these sources is either sent straight to the landfill or incinerated. Because the mismanagement of landfills is a large contributor to why this debris enters marine systems in the first place, sending them straight back to landfill does very little to fix this problem in the long term. Their collected debris cannot be brought into recycling facilities as there is far too many non-recyclable items to sort through it. Thus, without the ability to sort items, these solutions are missing a key portion of the problem they look to solve. The goal of our project is to build off of existing models to create a cheaper and more effective solution to the problem of ocean plastics. By including the novelty of sorting trash into plastics and non-plastics, the debris collected by our collector should be able to be sent to recycling facilities, as the amount of non-recyclables in the plastic bin will be at a much lower concentration and will be more easily separated into recyclables and non-recyclables. Our design consists of a floating body that is stationed at 2 points in a river, with funneling arms that draw the debris into our collection area. The trash will then be picked up by a conveyor belt, and as it moves along, our algorithms will run to detect plastics on the conveyor belt. When a plastic is detected, as it falls off the conveyor belt, a panel will open, allowing it to fall into the plastics bin. Otherwise, if plastics are not detected, the panel will remain closed and the debris will fall into the non-plastic bin. These bins will be removed by a forklift and brought off-site. The benefit of using 2 separate bodies in the river is that our design will not impede any wildlife or boats from moving down the river.
Next, we'll compare our design and our initial requirements. Overall, there are essentially 2 large overarching categories of capabilities that our system is supposed to exhibit. The first is picking up trash from the river, and the second is separating recyclables from that trash. For the first category of picking up trash, our system satisfies basically all of the capabilities. One capability needed for all the other ones is having a floating base to hold everything, as well as a frame to protect the other subsystems. The resulting design for the base and frame are capable of this, as backed by various buoyancy calculations and flow simulations. Another needed capability was funneling the trash. For this, we sourced a design that was used by similar river cleaners, and as such, we're confident it will work for ours. We also required something to move trash out of the river and into the bins. For that, we found a conveyor belt system to buy and adapted it for our system. Lastly, we needed storage capable of storing trash and being easily removed while also remaining stable on the rocking boat. The resulting storage bins and latching system satisfy both of those. While the design largely meets all the targets based on the previous examples, we were unable to simulate or actually test the full system at picking up trash. Before proceeding with any actual manufacturing, running a full-scale simulation or even a scale model testing would be imperative to find any possible faults that we missed. The second primary category is separating recyclable plastics from non-plastics. From the start, there were concessions that had to be made here in order to reduce the scope to be feasible. For one, we considered if we needed to implement a drying or jostling station to further separate the trash for processing. However, this would add too much complexity for what was already a very large project. As such, we assumed a sparse trash flow, which wouldn't need this extra station. Whether or not this drying and jostling step is actually needed is still unknown. Further testing with real trash in a river and analysis of trash density in rivers would be needed to answer this question. The other mechanical portion of the separation, the panel system, met the capability it was designed for, and this was physically portioning trash into either of two bins. The system had no large difficulties in design, so we're confident it can perform the task, and we will be testing on a prototype to actually confirm it can. For the algorithmic and sensing side of the plastic separation, there were a couple concessions that had to be made due to the fairly difficult process. Initially, we had a goal of using a SWIR camera to be able to detect if an object was plastic or non-plastic. However, due to the expensive cost of the needed camera, we pivoted to testing with a handheld spectrometer, for which we would aim to write an algorithm for. Unfortunately, the spectrometer was insufficient for our goal as it was unable to detect the necessary wavelengths, and it was also extremely inconsistent based on the shape of the object. These are issues that we wouldn't have had for the real camera. However, we were still able to use the spectrometer to detect some plastics and other materials in very flat scenarios. Due to the inadequacies of the available equipment, we decided that the overall detection of plastics was not going to be feasible during our remaining time. As such, the scope was pivoted to instead use a color detection algorithm, which would mimic what the plastic detection algorithm looks like. While we believe this algorithm is similar enough such that it would translate to the SWIR camera, this would still need to be tested on such a camera to confirm it. Another part of the algorithm, which would be needed for the actual design, is a computer vision system for object detection. The goal would be to form an object mask and track its position. We have developed an algorithm for webcam, which would pretty easily be translated to our design camera. While it is able to track similar objects on the conveyor belt background, it is still insufficient in detecting objects layered on top of each other. Overall, on the mechanical end, all the designs that we made ended up satisfying their intended capabilities. On the algorithms, again, there were definitely a lot of issues and unknowns which had to be explored early on, and so we didn't have much time at the end to do actual designing. The scope had to be reduced, but the resulting algorithms are similar enough that implementing them on the real design would not be a big leap in logic.
Hello everyone, I am Oscar Knox White, and this quarter I worked primarily on the floating body subteam. We began this quarter researching the existing designs and seeing where we thought we could improve. Additionally, we looked into what materials were commonly used when designing aquatic bodies. Our initial design consisted of a platform that used large plastic barrels to provide the buoyancy to the rest of the body, with a frame to hold the other subsystems and provide support and cover to the body. For this design, we planned on using aluminum 6061 for the frame and platform, and high-density polyethylene for the barrels. These materials are commonly used for long-term aquatic equipment as they have high durability to environment. As we did not end up going with the barrels, we did not use HDPE in our final design, but aluminum 6061 is still the primary material for the frame. After making these selections, I began developing the frame of the body. I started with an initial CAD just to get a general idea for the shape. The design was angled on the sides with a truss along the edges to provide lots of support to the body. In this initial design, the dimensions of the body were far too large to reasonably continue, so I realized I would need to redesign it. It was also decided that the only loads being carried by this outer frame would be from the plastic separation camera, the conveyor belt, and the plastic separation mechanism. Thus, the strength of the frame could be lower than I initially anticipated. I also needed to determine a way that this could feasibly be manufactured, so I decided to use shorter individual beams that would be welded together on site. This next design shown, very close to the final design that we are using now. The only adjustments made to it are able to be seen in the full assembly, which I will show later on. I then moved on to try and work on the funneling design and got a bit of progress on that before we decided one of my teammates would be better suited to finish this design. From there, I began researching the anchoring of aquatic bodies and decided I would use concrete pylons with chains securing the body to them. These pylons are very similar to boat docks and can be easily installed in rivers using PVC piping. I then determined that the anchoring would be the largest load on the body, so I ran a simulation to verify that the body would be able to withstand it, which is shown here. This study is run with a load that is over 6 times what we expect the average drag force will be in the river, showing that the frame will certainly be able to handle the force of the anchoring. Lastly, I was put in charge of managing the full assembly CAD, which is shown here. Funneling mechanism shown is just a stand-in for the real one, as the CAD for that one is not publicly available. However, the anchoring chains are also not shown for the same reason. The difference between the frame I showed earlier and the final design are the mounting beams here and here being used to hold up the conveyor belt. Another thing I worked on that didn't end up being used was a small scale version of the floating body that we were going to use to demonstrate the movement of the body in floating water and to verify that our funneling worked. This was ultimately scrapped because the flow of the water likely cannot be directly scaled down in the way that we expected. Also, the anchoring system we are using is kinematically constrained, and thus the floating body will not move.
Hello, this is the base of the floating body. Its purpose is to carry the entire assembly on top of it and therefore provide buoyancy so that the system is not in the water. But this part of the floating body is meant to be in contact with the water and not allow too much drag to occur on it while also being big enough to house everything on it properly. The interior consists of a welded frame. It's made out of aluminum 6061 3-inch by 3-inch hollow square tubes. The exterior of it is covered in a 1/4-inch aluminum 6061 sheet metal, which is going to be welded over the interior welded frame. The material for these two sections was chosen due to aluminum 6061's manufacturability. It's easy to weld, and also it is pretty lightweight, cheap, and also strong enough to carry everything. It is also very good and anti-corrosive against salt water. The floating body base weighs about 1,100 kilograms, and its volume provides about 54,000 newtons of buoyancy. So with this, it is able to support the full assembly on top of it about 1.5 times, since the full assembly's downward buoyancy is about 36,000. So this is more than enough to carry that weight. Its design was influenced by a catamaran style hull. This allows it to reduce a lot of drag since that center section is empty and allows water to pass through without any interference. It was also chosen to minimize weight. The welded style design was meant to provide enough strength so it doesn't collapse on itself, but still very lightweight since it makes an efficient use of space. And the sheet metal around it is meant to create the volume necessary to provide the buoyancy it needs. The funneling mechanism is meant to allow trash to be slowly funneled towards the center of the floating body, and therefore for trash to load onto the conveyor belt. To achieve this, we're going with Elastic's Permafence. It is a product meant to contain trash and other debris on rivers. A similar product has been used by other river cleaners such as Midget Trash Wheel. This one in particular is designed to be low maintenance and very durable. So therefore, one only needs to install it once and it can be there as a permanent solution. Very little maintenance. As for mounting solutions, it does require something different than used by Mr. Trash Wheel, for example. Mr. Trash Wheel uses a similar product, but they mount it on both sides of the river. So therefore, a similar product does need to be purchased by them. However, since ours is only going to be mounted on one side of the river, whereas one side of it is going to be free in the river, we need something to be able to anchor it. And that's precisely why we're going with Elastic's Terra Twist anchoring system. What this does is you install an anchor into the ground on one side of the river, and a rope is able to hold the free end of the permafence. And this will be done so that that rope doesn't have any contact with the trash and is floating above the river and doesn't interfere with any passing debris.
How we are going to pick up trash from the ocean, we looked at how other similar market products accomplish this. Looking at both Mr. Trash Wheel on the left and the Interceptor on the right, both utilizes a cleated conveyor system to move trash from the water and onto their system. So since they were successful in this, we looked to adopt a similar system for our design. For our design, we are using two conveyors. One is inclined and the other is flat. To narrow down our scope, we decided to buy the conveyors off the shelf. The incline conveyor is the GOFP 2000 cleated conveyor from MK North America, which mimics the same purpose as the other competitor's design. And the flat conveyor is from wire belt, which includes a wire mesh belt that allows for excess water to drip out and is an ideal material for wet environment. The reason why we decided on these two is because they're both food graded for wet environment. They're also fully customizable in size, and they both include a variable speed controller. We conducted a motion analysis using SOLIDWORKS to analyze what angle is needed for the incline conveyor and to see the size range of items the conveyor belt can pick up. Because there are some trade-offs between using a steeper angle and a shallower angle, we ultimately decided on an angle of 30 degrees because it would save us on cost and would not heavily affect the system capability. A higher angle would reduce the ability to pick up trash, but it would shorten the conveyor to save cost. A shallower angle would increase the ability to pick up trash, but would lengthen the conveyor, which drives up the cost. For the simulation, because SOLIDWORKS took an extremely long time to calculate the movement of multiple objects, such as in this study, we had to simplify some aspects of the simulation. For the water, because SOLIDWORKS did not have any fluid dynamic options, we mimicked the water using a conveyor that moves the object to our conveyor system. We also had to simplify the cleated conveyor to only one paddle because the simulation included many moving objects, which was taxing on SOLIDWORKS and would crash on multiple occasions. But from the analysis, we ultimately found that the conveyor can successfully pick up objects with heights of up to 0.1 meters because of the paddle. Because the water was modeled as a flat conveyor, we could not test rounder objects as they would get stuck in the pseudo water. As to how we are connecting the conveyor system to the floating body, we're using a square mounting bracket. The bracket is wrapped around the legs of the conveyor system and is bolted to the floating body. The bracket is made out of 316 stainless steel, which is commonly used material in marine applications because of its high strength and high erosion resistance. The bracket will be constructed with a square tube that is welded to a sheet metal and also include 12.5 millimeter through holes for screws and bolts to go through. To test the brackets, we conducted FEA analysis. Since our design is deployed on rivers and is posted to remain stationary, the FEA analysis done was a static study. Since the design of the floating body experiences about 300 newtons of drag force, we applied that same force to the X and Y direction of the skeletal frame of the conveyor. The yield strength of stainless steel is around 137 megapascals. So from the FEA analysis, the bracket has a high factor of safety value, which we can ensure that the brackets are sufficient enough to contain the conveyor.
Hi, my name is Tommy, and I was responsible for the mechanical plastic separation mechanism. There are two main parts to this. The first is the design that's going on the full boat. This was a start to finish design, so they included research, part selection, CAD drawings, strength analysis, and FEA. The second part is the prototype. This was downscaled from the full design and was made to be easily manufactured given our circumstances with limited materials. Again, this included CAD, manufacturing, assembly, and troubleshooting. With that, let's jump directly into the CAD models. So here is the CAD model for the design. As you can see, we have 4 panels here and they all move independently. They can move in either two positions, either this closed position here or 45 degrees into this open position. In this open position, any recyclables coming from the conveyor belt will fall into this gap and land into a bin for the recyclables. In the closed position, any other trash that is not recyclable will simply slide onto the panels and then off of them into the trash bin. The reason we have 4 independent panels is that it allows us to separate any trash that is side by side. Say we had a piece of trash on the right that isn't recyclable, but a piece on the left that is recyclable. We could open this panel on the left while leaving the other panel closed, allowing us to put both of them into the correct bins. With that, let's jump directly into some more details on the mechanism. Going right to left, we have a brushless DC motor, which was selected to provide the necessary torque and speed to rotate our panel. We have a sheet metal bracket just to hold the motor to the base. We also have a coupler here connecting the motor to the shaft. This shaft sits between 2 bearings, and these bearings are also embedded into a bearing block, which allows it to be mounted to the base. Connected to the shaft, we have these 2 universal mounting hubs, and these just provide an interface so that we can mount our bracket onto the shaft. Lastly, we have our panel connecting to this bracket, and so everything's basically one solid unit, which will rotate with the shaft. There were 2 big considerations during the design effort. The first is to keep things as low cost as possible. Part of this meant that we opted to use as many commercial parts as possible rather than designing them in-house. The only parts that are designed in-house and have to be manufactured are this bracket, and this panel. And these are pretty simple sheet metal parts, and so they'll be a lot cheaper to produce than something like machine parts. The rest of these parts are, of course, commercial parts, and that provides us a lot of cost savings. We've also opted for mostly bolt connections rather than welded. This means cheaper assembly, but also easier and cheaper maintenance down the line. The second big consideration was waterproofing. Our system does have to run in a marine grade environment, and we do expect some level of saltwater spray on this entire system. Therefore, for the parts that we selected, materials was an important choice. We decided to use stainless steel 316 for many of these parts, and aluminum for many others. Stainless steel 316 is marine grade, and so it doesn't rust the same way that normal stainless steel does, and aluminum also does not rust, so we expect it to last very long in the marine grade environment. The motor here is also IP65, water resistant, and saltwater resistant. We did spend a lot of effort in choosing the correct motor. We went through a lot of different options, including trying to make a DC brush motor waterproof. In the end, we just ended up selecting this brushless one because it provided the waterproof capabilities that other motors simply weren't able to. If we zoom out here, we'll see that the 4 panels are actually slightly different in the way that they're designed. The arrangement here is necessary due to some of the space constraints that we have. Nonetheless, actually all these parts are all the same, including the brackets and the panels, and so this saves quite a bit on manufacturing costs because we're not doing one-offs for every single panel. Lastly, we have this mechanism covered here. Initially, this was designed to help with the waterproofing efforts, but our design didn't end up needing it. And so the primary purpose now is to protect against any debris that might hit the motor or hit the shaft and cause damage. Jumping over to the CAD for the prototype, we have a pretty similar design here. The main difference is that all these parts are now going to be out of 3D printed plastic instead of the aluminum and stainless steel that we were working with before. We still have a couple commercial parts, but now many of these are basically 3D printed or cut out of acrylic. We've also swapped the motor here. This is just a normal kind of cheap servo motor that isn't waterproof. We don't care about waterproofing for the proto, and the servo motor's a lot cheaper and a lot easier to control. So here's a video of the prototype. So while we haven't done any substantial testing yet, we have validated that the system does move fast enough to represent our design, and so any testing that we do on it should be very representative of what we expect on the actual design.
Hi, my name is Juan Diego, and I'm responsible for the electrical end of our project, with a main focus on the plastic separation subsystem, which could basically be broken down into two main parts, a prototype and a design. On the prototype end, I was responsible for selecting components, designing and prototyping our circuits, and hardware debugging. I was also in charge of writing basic scripts so that we could run our servo motors for testing purposes. On the final design end, in terms of the component selection, aside from the microcontroller unit we would use, which I chose, the component selection was done by my other teammates based on calculations they made regarding our full design. And after knowing all the necessary components, I was able to get the power requirements for the entire system and created a simplified diagram of the main electrical components of our full design. So let's dive into the prototype first. For plastic separation, the components of importance were the material detection camera and the motor to drive our panel, depending on what the camera detects. To simplify prototyping, after some research, I decided to go for a servo motor, since it provides the necessary torque without the need for a motor driver and has easy connection to microcontrollers. And at first, went for a camera module that has good compatibility with the microcontroller we were using, which was an Arduino Uno. First, I built a fairly easy servo motor prototype using an SG90 servo, and then I helped Trevor, another teammate, build the camera module circuit, which was a bit more time consuming but simple to make with the circuit diagram we had. Then, integrating the two together was fairly simple on the circuit end. However, the issue with it was that it provided some challenges for the software side, since it would be hard to upload our algorithm directly into the Arduino, as it used Python for the image detection, and Arduino doesn't normally support Python. Therefore, for our second prototype, after talking to my software counterparts, we decided to use a webcam directly from a laptop to give input to the Arduino, as this would allow for Python to run. This worked in my favor too, since it greatly simplified the camera circuit to a simple USB connection from the laptop to the Arduino. The challenge then was creating the circuit for the final servo we used for prototyping, which was an LD20MG servo with enough torque to drive our prototype panel. Since this was a bulkier servo, it required an external power supply, but after some research and help from one of our TAs, I was able to create a minimalistic but effective circuit to move our panel, which you can see a video of to the right. This mainly shows our panel working, but at the end of the video you can see in the upper left corner that the breadboarding is very simple, and that blue blob that you see is our 7.4 power supply. Now, in terms of the final design, for our power requirements, the following components that we had for the full design were two conveyor belts, one flat and one cleated, an Ankur's plastic detection camera, 4 brushless DC motors with waterproofing, and a waterproof Sony camera, which we used 2 of, one for the plastic bin and one for the trash bin. This gave us a total power of 888 watts, and assuming a runtime of 12 hours per day at full power, we would be looking at 10 kilowatt hours for the power consumption. Finally, we had an electric component diagram which I designed. Assuming we would run from a power line, which you can see from that brown box, which represents a 24-volt power supply, we would use it to run our 24-volt belt and the 4 brushless DC motors. Then we would have 2 converters, one from 24 volts to 16 volts, so that we can run the Ankur's plastic detection camera, and one from 24 volts to 5 volts, so that we can run our 5-volt ARM microcontroller unit and the trash bin cameras. Additionally, you can see from the arrows, mainly the red ones, the plastic separation input and output, where the input is from the plastic camera going into the microcontroller, which would then control the motors. And you can also see from the blue arrows how the stoppage for the conveyor belt would work, depending on if the trash bin cameras see if the bins are full or not. With that, I end my section and on to the next one. Thank you.
All right, this is Sash, and right now we'll be going over the system design, how the components are wired together, and the specifics of the material classification algorithm. In the final product, everything will be controlled by a single microcontroller. Input will be received through a hyperspectral camera in the form of a 3D video feed. The 3 dimensions, of course, are 2 dimensions for pixel position, and the 3rd dimension will be spectral reflectance information, aka the reflectance of each wavelength for each pixel. And the hyperspectral camera will be controlled using an API to just record at all times, and the microcontroller will use the images to detect objects within the images and classify what material each object is, whether it is plastic or not. The microcontroller will also be telling the conveyor belt to move at a constant speed, and it'll control the flaps to move to the appropriate positions based on what objects are coming in, what positions they are, and what materials they are. And the output of the system will be the objects being dropped into the different bins. So this is the control flow for how the system operates. Assuming we are looking at the conveyor belt top down and the conveyor belt is moving to the right, then the objects will approach from the left side and end up in bins on the right edge. So first thing that'll happen, an object is detected on the left side of the image. First, not the whole object will be detected, only the right part of it. So the system will wait until the object is fully inside the boundaries of the image, and then it'll use the pixel reflectance information to classify the object. Now, the conveyor belt is moving at a constant speed. So once the object is classified as plastic or not, the system knows how long it needs to wait before sending the signal to the flap to move to the appropriate position. Because each object will take like a set amount of time to move to the edge of the conveyor belt since it's moving at a constant speed. And once that happens, once the object is appropriately in the right bin, the system will wait for the next object to come up the conveyor belt and repeat the process again. One case is, what if the objects are too close together for the flap to flip fast enough for it to drop the 2 objects into the right bins? Well, since the conveyor belt is moving at a constant speed, the system knows what the length is for the objects where the objects are too close together to be appropriately sorted. So in this case, it'll figure out whether it's more plastic or more non-plastics, and then just send them all to the same bin, all the objects that are too close together to the same bin. So we attempt to mimic this control flow and this design in the demo. So input will be received through a webcam instead of a hyperspectral camera, since those are prohibitively expensive. And instead of like a specific webcam API, we can just control it using CV, like OpenCV on Python. And the image processing is done on a laptop, and the flap control is done on an Arduino instead of using one microcontroller. So in this sort of setup, the Arduino is the dumb one, and it literally just controls the flap. The laptop does all the image classification, does all the thinking, and it just sends a signal to the Arduino when it needs the flap to move. So it still mimics like the conveyor belt, because we're not actually building the conveyor belt, we're just kind of mimicking it using like manually moving objects along with our hand. But the laptop will still know that there's like a constant speed. And then after it classifies what material the object is or whether it's red or not, it will delay an appropriate time before sending the signal to the Arduino for the flap to move. And the laptop to Arduino communication happens using the serial, and Arduino has libraries to control servos, which is how we control the flap to move in the right position. And the output will still be what bin the object is dropped in. And for this demo, we won't be classifying plastics or non-plastics, since we can't with this equipment. we're going to be classifying what color an object is, whether it is red or not. Okay, now for the material classification. Essentially, how we're going to approach this in the actual product is using the hyperspectral image. We'll get all the spectral curves from each pixel, and then we'll kind of average them out to find what like the average curve for this material looks like, for this object looks like. And we'll also store a database of the spectral curves of all the common plastics. And then we'll extract two features. One, we'll use the peak seeking algorithm to find the wavelengths of the peaks. And two, we'll find the spectral contrast angle of each of the sample and as compared to each plastic in the database. So what the spectral contrast angle is you treat the spectral curve as a vector where each kind of wavelength is a different element. And then you use like a kind of distance algorithm to find out what like the contrast is between two spectral curves. And it basically tells you how similar two materials are. So when we're analyzing a sample and trying to classify it as plastic or not, we're going to use this peak seeking algorithm, and we're going to find the spectral contrast angle compared to each like of the common plastics in the database. And we'll plug these in as features into a machine learning model. Excuse me. And if we find a match, we will send the object to the plastic bin, and if there's no match, we'll send it to the debris bin. Excuse me. So for the demo, we try to mock this as closely as we can, except with the link square. Now, unfortunately, the link square doesn't provide us with the wavelength range that we need to actually classify plastics. And it also doesn't have like the wavelength resolution that we need because it's susceptible to like surface characteristics like curvatures and like spikiness. And it only really gives consistent responses for flat materials or like fluid dish powder type materials. And these issues aren't present in an actual hyperspectral camera. And the other thing is the spectral response that the link square provides is very affected by the light sources within the link square. So there are always going to be three peaks, one at 450, 550, and 700 nanometer wavelengths. And we have to use these peaks, the heights of these different peaks, to figure out what material it is. As opposed to an actual hyperspectral camera, we'll have a sort of like flat-ish curve, and then they'll have peaks where more light is reflected. So the way we approach it for the link square is we use the height at the 450, 550, 700 nanometer wavelengths as features. And we also find the spectral contrast angle compared to each material in the database. Right now, this is working for two materials. Sandpaper 180J, which is sandpaper made out of aluminum oxide with like 180 roughness, and salt. And we actually can achieve 100% accuracy for differentiating these two materials. Obviously, this still needs to be expanded to more materials, and to make this work, we will be testing different features, like perhaps plugging in every single wavelength as a feature into the machine learning model instead of just four features where it's the reflectance at 3 different wavelengths as well as spectral contrast angle. And we will also experiment with other ML models because other kind of studies that use the link square have found great success by using SVM to classify materials. But right now, this is using just like k-nearest neighbors. It's gotten 100% accuracy, but again, this is only for 2 materials, so take it with a grain of salt.
Hi, I'm Jennifer, and I'm gonna talk about plastic separation. It has 2 main parts. First part, real-time object detection on black moving conveyor belt. Second part, plastic detection, which we will be implementing the assumption to detect whether an object is red for the demo. We will be mocking how a hyperspectral camera works internally for the algorithm. For object detection, we try 3 different methods. First one, we apply HSV inverse thresholding. We will convert RGB scale to HSV scale first, and then extract the range for color black, and do the inverse range for other colors, which will be seen as the object. For example, if in this case, 1.5 to 2 is colored black, then we will find the ranges on 0 to 1.5 and 2 to 4 and concatenate these two together. And when we're doing the testing, we can see on the green apple and banana image, it is not working very well. So we tried the second method, which is O2 thresholding. It's based on calculating threshold on class variance and convert RGB image into binary. The first image is the red apple image on the left. The middle, the middle image is detecting a coin on a white background. And when we introduce noises such as shadows, we can see it will be regarded as an object as well. And both methods require image capturing during real time, then make the analysis, which doesn't serve our purpose, which is detecting the object on a moving conveyor belt. So then we adopt the method of background subtractor in OpenCV. The background subtraction uses a machine learning algorithm to find out which part of the image changes from frame to frame, identifying the moving sections as the foreground and the static sections as the background. And this works for our purpose since the conveyor belt is all the same color, so the pixel values will only change minimally. We will see the pixels in the foreground mask and perform color detection on them after. So due to shadows and lighting conditions for red objects, the R value in RGB may not be the highest value. Using the raw pixel value to classify the color is not a robust method. Therefore, we convert to HSV using a formula dependent on the maximum and minimum out of the RGB values to normalize for lighting conditions. Since HSV is based on ratio, this mimics what we will be doing to identify peaks in the real plastic identification algorithm with a hyperspectral camera. We also plan to use a color contrast angle based on HSV to compare each sample to typical red HSV values from a database to identify if it is actually red. This is to more closely mimic the spectral contrast angle we will be using to help identify plastics in the real plastic identification algorithm. One concern that we haven't addressed in our demo is how to deal with transparent objects. In the real system, the hyperspectral camera would provide a response to ultraviolet wavelengths, which are still reflected by transparent objects. We will use this to detect transparent objects such as plastic packaging and bottles.
Hi, I'm CJ and I am responsible for the storage subsystem. Initially, we wanted to buy a pre-made storage bin from a manufacturer to reduce the cost, but it was too tall, so it does not fit into our system. That's why we decided to design our own storage. The storage has a dimension of 1.5 times 1.5 times 0.67 meters. It has a 1 cubic meters volume capacity. The material choice is 316 stainless steel sheet. The reason we choose stainless steel is because it is very corrosion resistant and it works very well in a wet condition. The thickness of the steel sheet is 14 gauge, which is about 2 millimeters thick. The storage will be paint coated in blue for recycling and green for trash. The storage will sit on the floating body base and there are 2 forklift buckets at the bottom. The storage is moved using forklifts. It is transported using a boat with a flat loading deck to the land and be empty. There are small holes at the bottom of the storage bin, which allows water to drain. There are two Latch-Style toggle clamps on the storage, one on each side of the storage. Its material is also stainless steel. According to manufacturer's spec, it has a 2,000 pounds holding capacity. Its function is to increase the normal force between the storage and the floating body base, and thus increases the friction. It helps restrict movement of the storage on the floating body. Next, there is a field level detection camera on each storage. We have designed a camera housing which is material is plastic. It is connected to the storage by an adjustable friction hinge. The view angle can be easily adjustable, and it is easier to replace the camera if needed. In terms of camera, we are using an Ecamm 82, a Sony Starvis IMX4 4K Ultra HD USB camera.
All right, so my name's Trevor Gomez. I'll be talking about what I've worked on this quarter. My work goes across a couple different subsystems, so we'll be jumping around just a little bit here. So to start out, I did a lot of work with the 07670 camera. This camera was originally intended to be used for both the plastic separation prototype and the storage system on our full design. So you can see some of the wiring that I had to do here to set up this camera, as well as an image taken in grayscale. This can be saved directly through a simple serial readout program and output a bitmap of pixels, which could be sent into the blob detection algorithm. This unfortunately was a little slow and needed to be phased out, which other group members will be speaking about. I also did some work with the real plastic separation camera that we would be using. This camera was out of our price range for actual testing, but nevertheless needed to be on our full design. We originally had a camera that had a smaller wavelength range, which we realized was not quite large enough for our algorithm to work. So instead, I researched and found this camera, the Acro CDQ 640, and this has a very wide range. You have visible at 350 all the way up to infrared at 2000 nanometers. It also has a wide angle lens with over 90 degrees field of view, which means that it can see the full conveyor belt if there are two of them at just above 0.4 meters over the conveyor belt, which will be mounted, as you can see here on the right. This goes directly through one of the aluminum crossbars already built into the floating body and can be screwed in from the side. The wires can be go in from the top, and the lens hangs out of the bottom. This camera is built for outdoor use, so there's no need for fancy lighting or anything for it to function. And the only thing that's sticking out of the aluminum is the lens, which is waterproof, so no need for waterproofing there. I also took on a role of managing the budget for the whole system. Looking at it by subsystem though, we have the conveyor belt sitting at about 13,000, plastic separation at 40,000, floating body at 20,000 before labor, and storage at 5,300. We estimate that labor cost to be around $100,000, split up mostly between the floating body, which has a lot of welding, and the plastic separation, which requires some assembly. Still, the total cost of the entire system sits under $200,000, which is amazing compared to our competitors whose costs were all over $800,000. Finally, I've been in charge of figuring out the prototype testing. So we will be having two tests. The first will be the computer vision metric testing. We'll be looking at accuracy first and foremost in percent missed, percent false positives. The goal here is less than 10%, as our competitors claim 90% accuracy for plastic sorting. So we want to get under that. We also want to know the distance between objects necessary in millimeters for detection. And our goal is to be under 5 millimeters to match that of the mechanical system. Speaking of the mechanical system, we'll be testing that same minimum distance for successful separation. Again, our goal is 5 millimeters based on our conveyor belt speed of 0.2 meters per second. And our demo or live test is shown here on the right. We will be pulling a black bed sheet to simulate our conveyor belt with our webcam mounted above it at about 35 centimeters based on its field of view. The plastic separation panel will be at the end of this table that we're using and pushing things into the two storage bins at hopefully our required speed. I'll now be speaking about the conclusion of our project. So first question is, did we solve our problem? So we successfully created a floating river collector, which actively separates plastic on the river from collected trash so that it doesn't need to be sent to a plastic sorting center. In many cases, trash collected wouldn't be sorted at all. It would all go to landfill, creating a bigger problem. We also achieved this all while keeping a much lower cost than our competitors at $200,000 to a comparable $800,000. Our collector is also hands off for operators until offloading, which means that it's able to collect the trash, sort, and identify when it's full to tell an operator that trash and plastics need to be offloaded. That being said, some things that our predecessors did right, we were able to take and adapt to our own, such as the funneling mechanism, using a cleated conveyor, and things of the sort. Now, there are some things which we would do differently next time. First and foremost, if we had a lot more time, we would do a lot more experimentation and prototyping. For example, the blob detection algorithm could have taken a lot more fine tuning. Same with our plastic sensing. We would have loved to get a lot more data, as well as just iterations with that sensing algorithm. We would have liked to test our funneling mechanism as well on some body of water, whether that be flowing or stagnant, just so we can make sure that trash is coming in as we intended for it, and it's not going to break off. We also would have loved to test our trash piling up issue. Basically, if our panel is only flicking to one storage or the other, there might be some piling up issues where those bins aren't filling all the way up, and we would have loved to test that. Finally, it would have been wonderful to make a full prototype for our conveyor belt so that we could test a full body thing on, perhaps even on a body of water. Some other things here. We never were able to identify a good power source other than the batteries. We originally talked about using a water wheel or perhaps a solar system to power this, but we didn't have enough time to look into this. We also would have liked to do more river research earlier on in terms of flow speed, river height, how they're affected by weather. The LAA River wasn't particularly well documented, and we perhaps should have picked a different one in hindsight. We also, speaking of rivers, would like to have done a better flow simulation. Past groups had used Flow 3D or other paid softwares. We didn't have access to this, but we would have liked to use it if possible. Our plastic separation system doesn't directly solve what it intended. While the mechanical mechanism works as intended, the sensing system ran into a lot of research and rework issues. We do think that it is feasible to achieve the levels of plastic sensing which we originally were setting out for, but only implemented some portions of that design. Finally, we should have started with waterproofing measures in mind instead of trying to waterproof things that we had already built. But overall, I think we still had a very successful project and are proud of our final design. So thank you for listening to our final design review.